Welcome back. For the final part of today's lecture, we're going to go beyond univariate Gaussians. So let's recall, we're going to do one of these, at least the first one, using the same type of framework that we did at the end of the last segment, which is known as coin press. It's called coin press for confidence interval based estimation, essentially, private estimation. So we described it instantiated for a very specific setting, but it can be applied to much more general settings as well. And we're going to try to describe it as abstractly as possible, show how this fits into the private mean estimation, univariate mean estimation setting, and then I'll describe to you how we use it for multivariate mean estimation. So, okay, so like here's the algorithm, or here's the framework rather, and we're going to go step by step. So the first thing we do is, the idea is when we're doing coin press, we'll always keep an sort of some confidence interval, or some confidence set rather, which is going to contain the true parameter that we're searching for with high probability. So for example, like at the beginning, we're going to start with mu is in minus r, comma r. So the way the framework works is we start by clipping the data. So we do this based on the confidence interval containing the parameter. So, I'm trying to describe this, to be clear, I'm trying to describe this as, abstractly as possible so that we can find out what the bare minimum things we need to know about the distribution and the setting in order to apply it to more general settings. So again, the first thing we're going to do is clip the data. And we do this based on the confidence interval containing the parameter. So yeah, like I said, we start with the fact that mu is in, say, minus r to r, and then this combined with the tail bounds of the distribution class. For example, like remember that we had the fact that this is essentially where the widening by the O of square root log n. This came in just because we were using a Gaussian. In particular, a Gaussian has very, fast decaying tails, and that's why we got such a small, widening of the intervals. But we'll see later how we'll have to widen them more potentially. So that's the first step. Clip it based on these two things. The next thing is compute the empirical estimator for the quantity and add noise proportional sensitivity. So for example, in the mean estimation case, you just compute 1 over n summation of xi, f of xi, I guess technically, and you add noise proportional to the sensitivity. So plus Laplace. And this is going to be bounded just based on the fact, based on the width of the clipping interval. So how wide the clipping interval is, the term that appears in the numerator here. It's kind of obvious here how the sensitivity is bounded because of that, but in some cases it might not be quite as trivial. And kind of the main step where all the magic happens is the third step, where we define a new confidence interval centered around this estimate with a width based on the sampling error and the noise added. So remember, centered around this estimate, in this case it'll be z. And the width is based on the sampling error. So the sort of error in this quantity, that's the sampling error, and the error based around this. So what we need here is that the width, this term will imply some sort of error in the, some sort of error with respect to how far it is from the true mean. And this will sort of indicate another type of uncertainty due to that. So like roughly speaking, there's some point z, and then quantifying the sort of uncertainty due to the sampling, that'll give you one interval, sort of something like this. And then quantifying the error due to the noise addition will give you another source of noise. And then after you do this widening, then you'll sort of have the guarantee that mu falls somewhere within this sort of extended interval. So the true mean falls somewhere in here. So yeah, that's the entire sort of one iteration of the algorithm. We sort of showed how these all these sort of bits and pieces which are left a little bit abstract here are sort of filled in based on the specifics of our setting. And all these really needed was the fact that we knew what a distribution class is, that is here it was Gaussian before, and that we could compute tail bounds on how big the deviation will be for the noise that we're adding. So putting both of these together will give us some sort of interval here. Okay, so that is the case instantiated for just like private mean estimation for a univariate Gaussian. Let's see, what we'll see what happens, how we can apply this for a multivariate Gaussian mean estimation. In fact, let me just sort of take some of this stuff from here, because this is exactly, we were a bit generous on space here. So yeah, that's the goal, and let me just grab this picture which we're going to use. Right, so here, using the same type of framework, this is the type of theorem you can prove instead, and we're going to see just exactly how you do this. Let me just copy it, in fact. Whoa. Zoom out. Sorry about this. Let's see, get rid of this. Copy this. Okay, so let's see how exactly we can prove this theorem. And first of all, I guess before we even do that, let's see what the theorem even is. So the theorem here is there exists a differentially private algorithm which estimates the mean of a multivariate Gaussian this time. So I guess I didn't say it here, but this is now going to be a multivariate Gaussian in d dimensions. And right, we say that, what do we know about this d-dimensional Gaussian? We say that the mean of this Gaussian is bounded by R. This is like different than before, where before we had that the mean is sort of an absolute value is bounded by R, but now we have that the L2 norm of this mean is bounded by R, related but not exactly the same. And we want to learn it now, not just to accuracy alpha, but what does that mean? Now we want L2 accuracy alpha. And the sample complexity will now be d over alpha squared plus d over alpha epsilon plus roughly square root d log r over epsilon. So let's just sort of circle in orange all the differences from before. So this essentially, these terms are the ones which are new. Perhaps these d's here shouldn't be too surprising. You go from 1 dimension to d dimensions, things will scale up by d. The last one might be a little bit the most unfamiliar one, just because it only scales up by a factor of square root d, but that's, I guess, better. And yeah, one thing is the fact that we only can handle epsilon delta differential privacy here. The reason is because that we moved from pure dp to approximate dp. Why did we do that? Is because of the fact that in terms of often when you move to multivariate settings, the Gaussian mechanism will be more natural, just because of the fact that your statistic will have an L2 sensitivity. In particular, if you move 1 point, this will affect the mean in L2 norm. So, right, that's kind of the issue in terms of why we use Gaussian noise instead of, why we approximate differential privacy instead of pure differential privacy. So, okay, let's see how we do it now. So the first thing we do is the fact that our confidence interval is now a confidence set or a confidence ball. So it's going to be, the mean will be in the L2 ball, which is centered at 0 and is of radius capital R. So the first thing we do is clip the data. And we're going to do this based on the confidence interval containing the parameter combined with the tail bound of the distribution class. So the first thing we know is that the mean is within this ball, so we're definitely going to clip to that, but we have to widen it based on the tail bound of the distribution class. So one easy thing to, well, one, it's not exactly easy to see, but like if you sample, say, y from n 0 I, then my claim is that the L2 norm of y will be approximately equal to square root d. Yeah, it's essentially saying that take a sample from a Gaussian, how far will it be from its mean, or say in this case the origin, it'll be about square root d away from the mean. This is kind of a counterintuitive fact that if you take a sample from a Gaussian, despite the fact that the PDF is highest at its mean, most of the points will actually be quite a bit further away. So, okay, all we're saying here is that, the fact that the points will be about square root d apart, far from the mean, and therefore we have to sort of grow this ball by square root d. In particular, we'll have sort of a tail bound saying that if we kind of have to clip at not just square root d, but O of, like first of all, square root d plus square root log of n. Similar to before, we have to kind of take a union bound to account for all of the points. So in other words, putting these together, we know that the mean is within this ball, and this is the sort of distance from a sample, from the mean to the sample. Then the total clipping, we will clip to the ball b to O, and then the radius will be r plus square root d plus square root log n. This essentially accounts for the points being anywhere, the points being within this distance of the true mean, where the true mean can be anywhere within this ball. It kind of grows it appropriately. Okay, so right, that's good. And the next step is just compute the empirical estimator for this quantity. This is going to be essentially the same thing as before, 1 over n summation of xi, plus this time we have to add Gaussian noise of appropriate magnitude, where, Gaussian, because like I said, this now has bounded L2 sensitivity because we're clipping to an L2 ball. Good. Now, the last step is to define a new confidence interval centered around this estimate with a width based on the sampling error and the noise added. So, right, what do we want to do? We want to really kind of quantify how much error is present. So how much error is present due to each of these? Well, one thing we have here is that the error incurred during this type of thing will be roughly, say, square root d over n. This is sort of a standard sampling error due to just for a Gaussian. If you take the empirical mean, then this is going to be roughly the difference between the distance between the true mean and the empirical mean, square root of d over n. And then we have to account for the noise in this Gaussian. So this is a little bit trickier, but how much, right, let's, I left this as a dot, dot, dot here, but let's actually write out what this dot, dot, dot is here. So the standard deviation and, the standard deviation will be, in each coordinate, will be something like r plus square root d plus square root log n divided by n epsilon. And this is just using the Gaussian mechanism. Essentially, since we're clipping to this ball, that incurs an L2 sensitivity of this much, so we need to noise proportional to the L2 sensitivity, divide by n, since it's normalized, and then epsilon is the epsilon term. And we're going to ignore the deltas because it's simpler this way. Okay, so that was a bit of a mouthful, but essentially the error in each coordinate is going to be this much, sort of by a standard Chebyshev bound. And since we're working in d dimensions, that corresponds to an overall error of square root d times that. So the overall error is square root d times, this quantity here, r plus square root d plus square root log n over n epsilon. And then, of course, we would repeat it. So the one thing that we want to really see here is how do we ensure that we make a constant factor improvement? Well, really the leading term here is going to be the following. Like if you look at which term is kind of the biggest, it's really, it could be, assume r is kind of much bigger than square root d. If that's true, then the biggest term will be square root dr over n epsilon. And in order to make a constant factor improvement, that is, originally we started with a ball of radius r. In order to make a constant factor improvement, we need that n is going to be greater than or equal to square root d over epsilon. Because, just say like 100 square root d over epsilon. The reason why is because this will shrink this ball by a significant constant factor, and therefore we'll have made progress in the same way we've made before, right, where we shrink it by a constant factor. And the idea is simply as before, we can repeat this a constant number of times, or sorry, repeat this log r times. If we repeat it log r times, then in fact we're going to be down to a ball of, say, significantly small radius, and we can just use a naive approach. This will get us down to a ball of radius r equals O tilde of square root d. So at this point, let me just note that since you do this log r times, similar to before, that by sort of composition, this time since we're using approximate dp, you can just use a naive or advanced composition, which will only pay a square root log r factor, and that'll give the right sample complexity in order to get down to a radius of O of square root d. Okay, so now the claim is, I haven't gone over this, but I claim that there's another naive approach which gets, error, the naive approach which takes n equals O tilde of d over alpha squared plus, essentially I claim that once you get down to a radius that's roughly this small, then you can just use a naive method and it'll all be okay. This will get you down to the sort of appropriate, this will get you down to the appropriate accuracy. At this point, you can use naive estimator. Okay, so that's just sort of like rough sketch. It's not fully detailed, but that type of approach will get you this sort of guarantee in terms of a multivariate Gaussian mean estimation. And to give you a sort of picture as to what that looks like, it's kind of similar to before, but suppose your data set is just shrunk in this tiny little thing here, but you have started with a large ball like this of uncertainty. You start with a big ball, and then you can shrink it down in one step, because this will shrink the radius by a constant factor, and then do it again, and so on, and eventually you'll get something which is fairly tight around the data set, and you won't be adding far too much noise. The same type of approach can be also used to get covariance estimation, but this is definitely beyond the scope of these notes because we've spent enough time already. So check out the paper if you're curious on seeing how to do covariance estimation. All right, and as sort of just a final sort of end to this today's lecture, let's talk about heavy-tailed data. I promised beyond univariate Gaussian. We went beyond univariate Gaussians. But now we're going to go beyond univariate Gaussians. That is, we're going to try to relax this assumption that our data is Gaussian, which is often a very strong assumption. Like, why would our data truly come from a Gaussian distribution? It's unclear. Right. So, like, we're going to try to relax that and try to go for something which is applicable in more general settings. So, first of all, like I said, we only have things for Gaussian data, but in fact, I claim that it actually works for sub-Gaussian data. So what is sub-Gaussian data? A sub-Gaussian distribution in particular is one where the tails die faster than a Gaussian. So like just to draw you a picture, suppose this is a Gaussian distribution, looks something like this. Well, a sub-Gaussian distribution would be a distribution whose tails die more rapidly. So maybe something that looks like this. It starts like this and then it dies very quickly. So the claim is that you could use the similar, like the reason why it's called sub-Gaussian is because you can see it kind of lies, the tails lie below a Gaussian's distribution's tails. So yeah, this is a sub-Gaussian distribution. Now the only things we used in the previous examples were essentially that the tails aren't too heavy, so anything we argued before we'll argue here as well. But however, let's see if we can do something for heavy tail distributions, which also arise commonly in practice. So what is a heavy tail distribution? So a p-beta distribution. This essentially says when, I guess we'll have to consider what are the moments of the distribution. A moment of a distribution, the kth moment of a distribution is essentially, let me write this as follows. You imagine you have x distributed from P, and you take x minus the mean of x to the k. This is the kth moment. And right, the idea is that with a sub-Gaussian distribution, here we have that all moments are bounded. The second moment, the third moment, and so on, they are all bounded, which sort of implies that the distribution will decay very rapidly in some sense. However, often this isn't the case. Suppose sometimes we only have distributions with, say, like some mean, and they have a bounded variance. So let's just go over a simple example and try to investigate this simple case. So suppose we know that simple example. In this simple example, we're going to just imagine first of all that mu is equal to the expectation of expectation of x, where x is drawn according to p, which is, say, in some interval -1, 1. So I intentionally chose this to be like, before we focused on the case where the range or the interval could be very wide, but for now we're just going to focus on a very simple case where the mean is known to be bounded between -1 and 1, but we want to estimate it even more finely than that. Okay, that's the one thing we know, and the only other thing we know is that the variance of the distribution, that expectation of say x minus mu squared, is bounded above by 1. Let's say it's just less than 1. This is all we know about the distribution, and we wish to privately estimate mu. So we're going to see why we're going to have to change our strategy a little bit. In particular, the lack of these bounded moments, higher order bounded moments rather, will require us to clip much more aggressively. Our previous strategy of not clipping any point will introduce far too much noise in the final step. So we're going to find it helpful to recall our, how we decompose our error. So let me just write what our goal is. We're trying to bound, say, the true mean minus some estimator of the mean. We're going to try to stick with the same general framework as we did before, but we're going to maybe account for the error a little bit differently. So this is saying that the difference between the mean and a noise version of our clipped mean, this will be upper bounded by mu minus 1 over n summation of xi plus summation of xi minus 1 over n summation f on xi plus this So let me recall, this decomposition. It's again using the triangle inequality. We have these errors that occur from three different things. This is the error due to sampling. This is the error due to this is sort of a new error, one that we've always sort of set this to be 0, but this is going to be due to bias from clipping. And this last term here will be due to noise addition for privacy. So, yeah, before a strategy was to try to choose the clipping function f so that this would be 0. But we're going to see that if we try that again this time, that's going to result in far too much noise for the third term, and therefore we're going to need to have this be non-zero, and that'll reduce this. But that's getting a bit ahead of ourselves. Let's see what happens if we try to choose a strategy which results in the bias from clipping being 0. So, okay, consider throughout this sort of example, we're going to clip to the interval -1 minus tau and to 1 plus tau. So essentially, we take our initial interval and we sort of stretch it out by an additive tau, where tau is some parameter to be set. So where will the points lie? Well, what type of concentration can we use for our points? So remember that essentially all we can do is say that the probability that x minus mu is greater than square root n is going to be less than or equal to 1 over n. So this is the only thing we can say about a point here, that the probability that it lands greater than square root n away from its mean will be 1 over n at most, just because of the fact that this is just using Chebyshev's inequality. It's square root n standard deviations away, and this will be 1 over n probability here. And in particular, you can sort of make this, if you add if you put a, say, 10 here, this will be 100 here. Okay, so by a union bound, this implies that this is like a reasonable threshold to clip at if you don't want to clip any point. Sorry, I'm getting a bit ahead of ourselves. Let's say that by a union bound, if you draw n samples from this unknown distribution P, then they're all in the range, say, mu minus 10 square root n and mu plus 10 square root n with pretty high probability. Let's say 99% probability. So let me just draw one distinction from what we had before. Remember when we were looking at sub-Gaussian distributions or Gaussian distributions, we had a square root log n here, but now we have to have a much wider interval than before. Now it's square root n. So this is quite wide actually. Okay, so the idea is if we want to result in zero bias, that is no points are clipped, zero bias sort of corresponds to tau equals theta of square root n. Okay, so we've got zero error for clipping, but let's see what sort of noise we would have to add. Recall that we would have to add noise proportional to the width of this interval. So the noise that we'd add, n, is equal to essentially Laplace of theta of square root n divided by n epsilon. So the width of the interval divided by n times epsilon. Now the thing is, let's look at how big the error due to all three of these things, sampling, bias from clipping, and noise for privacy, are. Well, it's not hard to see that the sampling error, as before, just by using a Chebyshev bound here, that will give you an error which is O of 1 over square root n, as before. that's the sampling. The bias thing, that we intentionally chose it to have 0 bias, so there's 0 error from bias due to clipping. And how big is the error here? Well, this will be approximately O of 1 over square root n times epsilon in magnitude here. So, okay, the total error that we have is upper bounded by the sum of these 3 errors. So just sort of looking at it, if we wanted overall to be bounded by epsilon alpha, then we need that this final term is going to be upper bounded by alpha. So 1 over square root n times epsilon is less than or equal to alpha. And this would imply that this would require that n is greater than or equal to 1 over alpha squared epsilon squared. So this is significantly larger than we had before. Before, recall, we had 1 over alpha squared plus 1 over alpha epsilon. So this is kind of significantly more in both of the terms. So that was not great. Let's see if there's something better we can do. In particular, the reason why we kind of lost is because of the fact that we really were particular about needing zero bias here. It turns out that by being more careful or more intelligent with our choice of how to choose the bias, we can actually do something better. So what will we do? We're going to, basically, there's a question of how, if we clip at a parameter tau, how much bias do we introduce? And it's kind of, we're not going to prove this today, but like, let me claim this. The fact that that's fine. So let me just claim that this magnitude here, so this is just a claim, I won't, again, I won't prove it. Clipping to, say, mu minus tau, mu plus tau, gives, what do we get? Right, how much, sorry, I guess what I'm trying to say is how much bias is introduced, how much error is introduced by this clipping operation if we clip to this interval. And it turns out that it's possible to show that this, the bias introduced here is going to be O of 1 over tau, roughly. Yeah, it's not too hard to prove this, but we won't do it here today. So, right, if we do this, then it's not too hard to complete the proof. In particular, we can see how to, optimally set tau in order to balance the noise with the bias due to clipping. So we'll just write it here. In fact, I claim that if we, no matter where we clip, the error due to sampling will always be the same because this doesn't depend on the clipping at all. So the error due to sampling will always be O of 1 over square root n. The bias due to clipping will, like I said, be bounded here. We can see my claim is that it's O of 1 over tau. And the noise due to privacy is going to be O of, tau is going to be the width of the interval. So it's going to be O of tau divided by n times epsilon. So yeah, these are the 3 sources of error, and the idea is we want to bound all 3 of these sources of error by alpha. So what does that give us? We want that 1 over root n plus 1 over tau plus tau over n epsilon is going to be less than or equal to alpha. So in order to do this, then we have to bound each of them individually by alpha. So, the right setting of tau would be, for example, tau equals, say, like alpha over 3 or something. And then based on that, you can see that we, to bound this term by alpha, we need that n is greater than or equal to O of 1 over alpha squared epsilon. So yeah, all we did was derive a magnitude of the error due to sampling, bias from clipping, and noise due to privacy. We tried to sum them all and bound them above by the target error. And then from there, we can just solve for what parameters we should set. So that just tells us we should clip essentially to, something which is of radius, basically alpha. We have an additional alpha in terms of how far we clip. And this gives us an overall sample complexity of n is equal to 1 over alpha squared times epsilon. So let's compare this 1 over alpha squared times epsilon with our previous bound. So our previous bound, this just had our previous bound when we had the sub-Gaussian case was, let me write it in a different color. Our sub-Gaussian case gave us a sample complexity of 1 over alpha squared plus 1 over alpha epsilon. And you can see here that it's increased to kind of like squash these two terms together into 1 over alpha squared epsilon. Now, that's kind of, it's more expensive now, but it's also necessary, I claim, and there's proofs for the lower bound as well. I just want to say that this essentially becomes more expensive, but this is also necessary. This is kind of natural because when you know less about your probability distribution, then you're going to naturally increase the amount of samples you take. So yeah, we showed these kind of bounds as well as lower bounds in higher dimensional settings in joint work with Vikrant Singhal and John Allman again. So yeah, that concludes today's lecture on private mean estimation. We kind of covered a lot of different settings. We covered, univariate Gaussians. We covered multivariate Gaussians. We covered non-Gaussian distributions. We even just mentioned a little bit about covariance estimation, which it works for, which we can do as well. But yeah, this is a pretty rich literature, and there's still a lot of stuff to be still done. So I hope some of this excites some of you to investigate it further.